Well, grade 12s, you have made it to the last concept or section within the section of trigonometry. So give yourself a pat on the back. We are almost done with this, and this concept is not a very long one. It doesn't take up a huge amount of weighting in any exam, and it's something that can be mastered if you are A, systematic, and B, good at algebra. Believe it or not, there's a lot of changing of the subject of the formula in these kinds of questions. So have a look at the 3 rules that you actually already know from grade 11. The sine rule, the cosine rule, and the area rule. Remember that in the sine rule, A over sine A equals B over sine B equals C over sine C. Those ratios can be flipped. You can say sine A over A equals sine B over B equals sine C over C. Right. Also remember that obviously the variables can change depending on the question given. And then last thing I want you to remember is to not overcomplicate questions. If you are given a 3D diagram like this one in the example, don't freak out, because in the vertical planes you can use your normal SOHCAHTOA and Pythagoras, and those are simple concepts that you've been doing for a very long time. So if you can work in the vertical planes, you will be working in right-angled triangles, and that will make your life so much easier. Okay, let's jump into this example. This diagram is of a birthday card with the given dimensions, and we need to find the length of PR. As you can see, PR is the diagonal of the rectangular side of the birthday card. It is also given that the angle in the horizontal plane, QRT, is 105 degrees. Now let's jot down the information that we know for sure. The yellow shows us that angles in the vertical plane are right angle triangles. So pop in those right angle symbols so that you know where you can use Pythag or SOHCAHTOA. Straight away you can see that if you're looking for PR, oh, another thing is that since this is a birthday card, QT will equal QR because it's folded in half, so they're the same length as each other. Now, we need to find PR, which will obviously be the same length as PT, since these rectangles are exactly the same size in every single way because it's a birthday card. Easy peasy, we just use Pythagoras. Don't forget to square root to get PT, and you end up with 30,7 centimeters. Don't forget your reason Pythagorean theorem. Right, once you have a value, it's useful to go and sketch it in the sketch. Go and write it down so that you can use it in the next question where you will most likely need it. Right, number 2 is asking us to find the length of RT. As you can tell, RT is now no longer part of the vertical plane right angle triangles. RT lies in triangle QRT, which is on the horizontal plane, which is not a right angle triangle. So we are going to use either the sine rule, the cosine rule, or the area rule to find RT. If you have a look at the cosine rule, it's useful to use the cosine rule when you have 2 given sides and their included angle. In other words, the angle that lies in between the 2 sides whose lengths you know already. And we know the length of QT. It has to be the same length as PU, right? Because we're dealing with a rectangle. So I can already say, I can substitute, and QR is the same length as QT. We've stated that already. So we can substitute in 18,5 in the place of QT. And in the place of angle Q, we substitute in 105 degrees and we get RT. Now, I'm jumping straight to the answer, but I would appreciate it if you can press pause and check yourself to see if you can get to that answer as well without using just one step. You are going to have to manipulate this equation to... Oh no, never mind. Apologies, I'm not going to restart this slide. It's mere substitution. You plug it in your calculator, you square root your answer, and you get to 29,35. Sorry, I'm really jumping the gun here. What I wanted to say there is for the next example, which is number 3. Right, first things first, let's write down the 29,35 in the place of RT, and now let's tackle this finding the size of angle RTP, number 3 over here. Right, we need to find the size of angle RPT, and we need to round off our answer to 2 decimal place. Now, if you have a look at angle RPT, you'll see that it is in the diagonal plane. This diagonal plane is not the vertical plane, it's not the horizontal plane, it's its own plane, and it's connecting RT to P. So we need to find that angle P marked there as that white arc. So once again, we can see that we have 30,7 centimeters as PT and PR, and so we can use the cosine rule again. This is where I would love you to please pause this video and you try and find cosine P. Make that the subject of the formula by yourself, and then find angle P, because I'm not showing you in this example how to make it the subject of the formula. As you can see, I've skipped that step, and I need you to know how to do that. And if you are struggling, you need to reach out to me. Please just show me and let me know, and I will gladly show you the step by step. But for now, to save some effort and time, I'm just like to run through the 3D trig concepts, not this algebra changing the subject of the formula story. Okay, so there we get angle P is 57,11 degrees. Beautiful. This next example is taken from the next activity because there are only 2 exercises on 3D trig, and I'm going to give you both of those exercises to do. However, you have today and tomorrow to complete them, all right? So if you struggling, refer back to this video, or please reach out to me. Tomorrow there won't be another video to watch. Okay, so this exercise is more relevant, or I feel more applicable to what I've seen in past papers. It's very useful to be able to write sides and angles in terms of given variables. In this diagram, we haven't been given any actual distances at all, and they've asked us to express angle D in terms of theta. Now, if you have a look, BD has been labeled as lowercase d, and CD has also been labeled as lowercase d. So we can conclude that that must be an isosceles triangle. Hence, I've labeled that little angle over there C1, and we can say that C1 equals theta. Our reason is angles opposite equal sides are equal. Great stuff. Now, using our knowledge of angles in a triangle, we can say that angle D is equal to 180 degrees minus those 2 thetas because of the sum of interior angles of a triangle. Great, easy peasy. Now we're asked to prove that AB, voila, AB is that beautiful vertical line. Vertical plane triangles are always right-angled triangles, so we can use SOHCAHTOA. Don't overcomplicate things. Don't overwhelm yourself. Go straight to what you know about AB, and that is that it is an opposite over adjacent in relation to alpha. All right, so let's work in that yellow triangle, and you will see that tan alpha is equal to opposite over adjacent, which is AB over CB. Now the issue, or the useful thing about CB is that it is the connector, the linking side between the vertical plane and the horizontal plane. So if we can find CB in terms of theta and D, then we can substitute that back into this little equation that I've just written down, tan alpha is AB over CB, and we can manipulate it in order to prove that AB equals 2D cos theta tan alpha. So let's work with that CB in the horizontal plane for now. Do you see that CB is directly opposite to angle D? And we have already found angle D in question 1. So that should make you realize that we need to use the sine rule. CB over sine of angle D is equal to any one of the other sides, because we have all the information of that triangle pretty much. So is equal to D over sine of theta. Now have a look at sine of 180 degrees minus 2 theta. Remember the cast diagram? Is that not just the same as saying sine of 2 theta, because 180 minus is quadrant 2, which belongs to sine? So my next line, I can actually just replace sine of 180 minus 2 theta with sine of 2 theta. Hey, hey, hey! I hope you are feeling as excited as I am about the fact that sine 2 theta is the double angle identity, so we can replace that with 2 sine theta cos theta. Beautiful. Now let's make CB the subject of the formula by merely cross multiplying or multiplying by the denominator 2 sine theta cos theta. And what do you know? The sine thetas cancel. Oh yeah, and now we end up with CB is 2D cos theta. Look how close that is to what the question is asking of us. So we've got something, that red CB in our first equation, the tan alpha equation, that CB can be replaced with 2D cos theta. And now we can make AB the subject of the formula by multiplying tan alpha with 2D cos theta. It's as easy as that. The reason you guys struggle with these questions is often because you leave them for last. You focus on say your general solutions and other parts of your paper 2 first. These questions also pop up towards the end of an exam paper, and by that stage you're generally tired and stressed out, and it's since we have section A and section B, I know you presume that the end of section B is definitely problem solving, is definitely really tricky, but I am so hopeful that if you just tackle these kinds of questions with a clear, fresh mind, you will be a-okay. Right, so do as much of example exercise 4.13 as well as exercise 4.14 as possible. They are not long exercises, and please let me know if you have any issues. Another thing I'd like to ask you to do is to please read over the examples. It will be in your to-do list, but read over the examples before these exercises, because it will give you extra tips and extra insight. Righty, grade 12s, well done. You are at the end. Good luck and enjoy. I concluded and it wasn't the end of the video. I'm so sorry. Last little example, using our previous knowledge, it's really straightforward. We now have to find the length of AB, but fortunately we already have an expression for AB. So they're telling us that D is root 2, cos is theta, and tan is alpha. So let's just substitute in those relevant values, and then you need to realize 30, woohoo, special angle, we'll deal with that later, but 75 degrees we can perhaps split into a compound angle identity, because 75 is a beautiful sum of two special angles being 45 and 30 degrees. Right, let's apply our double angle identity and then insert what our special angles are actually equal to. Once again, I'd like you to pause and try and solve this without the use of a calculator. If you are completely confused, reach out to me, but you should get root 3 minus 1 all over root 3 as your final answer. Okay, now we're done. Good luck with your homework.